Hello everyone, welcome back to my Continuum mechanics lectures. So we were doing tensor analysis and we will pick up where we left off. So last we started discussing the directional derivative of a vector. So that is Lu. L was our gradient of a vector. L operating on a vector u was limit s tends to 0 1 by s v of x naught plus su minus v of x naught. V of x can be written as v hat of xi, that is function of v as a function of the spatial coordinates or Cartesian coordinates. So taking u as e1, we had L of e1 as ei del vi hat by del x1. So in general, when we take L of ej, we have v del vk by del xj ek. So going on, so as L ej is v kj ek, taking a dot product with ei dot L ej is v kj k comma j ek dot ei. This is v k comma j del ki, which is nothing but v I comma j. What is this quantity? As we had seen in our lectures on tensor algebra, this is nothing but the components of L with respect to the ei dyadic ej basis. Therefore, Lij is vi comma j, and L therefore becomes gradient of v is equal to vi comma j ei dyadic ej. As we had seen before with the scalar function dv, taking a differential of v yields del v acting on dx. Therefore, this means that del v, gradient of v, is the linear transformation which operates on dx to give us dv. So let's obtain the components of the gradient or the form of the gradient using this definition as well. So x is xiei, therefore dx becomes dxiei, and therefore dxi is dx dotted with ei. V as a function of x can be written as v1 xi, that is v1 as a function of x1 x2 x3 e1 plus v2 xi e2 plus v3 xi e3. Now dv is written as del v1 by del xi, because this is a function of all the x's, dxi e1 plus del v2 by del xi dxi e2 plus del v3 by del xi dxi e3. The dxi's can be replaced with dx dot ei. Therefore, this becomes del v1 by del xi dx dot ei e1 plus del v2 by del xi dx dot ei e2 plus del v3 by del xi dx dot ei e3. Combining the terms, you can write this as vj by del xi dx dot ei ej. Written in terms of the dyadic product, this can be vj by del xi ej dyadic ei acting on dx. Therefore, this quantity becomes the gradient of v. So interchanging the indices I and j, we have del vi by del x j ei dyadic ej. So we have achieved the same result with this definition as well. So as we had seen, let's do this in a different document. As we had seen earlier with the scalar function, scalar field, that we can also uh, see, see the components of the gradient in polar coordinate system. So following the same procedure as before, that x can be written as r er theta plus zk. Therefore, dr becomes dx dot er, d theta becomes 1 by r dx dot e theta, and dz becomes dx dot k. Now v of x is a function of, is written in terms of components as vr r theta z er plus v theta as a function of r theta z e theta, and vz as a function of r theta z ez or k. Therefore, what does dv become? dv is del vr by del r dr plus del v theta by del theta d theta. Sorry, this one is This is still del Vi. We are still talking about the components, the component of ER. D theta plus del VR by del Z, again dz ER plus VR E theta d theta. So this comes from differentiating uh, the unit vector ER, because it is a function of theta. Then differentiating the components of, so we were, so this whole term is a differentiation of the whole term. This is theta, and similarly we have to do the same with this as well. So this becomes del v theta by del r dr plus del v theta by del theta d theta plus del v theta by del z dz. This times e theta minus v theta er d theta, because del by del theta of e theta is minus er. That can be seen from writing er and e theta in terms of cos theta e1, that er is cos theta e1 plus sin theta e2 in terms of the Cartesian coordinates. And finally with z, we have del Vz by del r dr plus del Vz by del theta d theta plus del Vz by del z dz. Okay. So as k is a constant unit vector, there is no differentiation of, and does not depend on r theta or z. There is no differentiation. There is no term like v theta er d theta or vr e theta d theta. So we take those terms, all the terms which have dr in them together, d theta in them together, and dz in them together. So let's write it. This is del Vr by del r er plus del v theta by del r e theta plus del v z by del r k dr plus del Vr by del theta er plus Vr e theta plus del v theta by del theta e theta minus v theta er plus del vz by del theta k d theta plus del vr by del z er plus del v theta by del z e theta plus del vz by del z k dz. Now dr is nothing but dx dot er, d theta is 1 by r d theta dot dx, and dz is dx dot k. So so we'll so taking this first term here, this is del Vr by del R Er dx dot Er, which can be written as del Vr by del R Er dyadic Er dx. Similarly, we will write the whole expression in terms of the dyadic product on the next page. So therefore, this becomes del Vr by del R Er dyadic Er plus del V theta by del R E theta dyadic Er plus del Vz by del R K dyadic Er dx plus 1 by R del Vr by del theta Er dyadic E theta plus Vr E theta dyadic E theta plus del V theta by del theta E theta dyadic E theta minus V theta. Was it V theta? Let's check. Yeah, it was V theta. V theta ER. ER dyadic E theta plus del Vz by del theta K dyadic E theta. The whole times dx and plus del V R by del Z ER dyadic K plus del V theta by del Z E theta dyadic K plus del Vz by del Z K dyadic K times dx. So dx can be taken out. We'll write this again on the next page. Taking dx out and writing the whole expression as del v acting on dx, the gradient of v acting on dx, we find that del of v is nothing but del vr by del r er dyadic er plus 1 by r del vr by del theta minus v theta er dyadic e theta plus del vr by del z er dyadic k plus del v theta by del r e theta dyadic er plus 1 by r del v theta by del theta plus vr e theta dyadic e theta plus del v theta by del z e theta dyadic k plus del vz by del r k dyadic er plus 1 by r del vz by del theta k dyadic e theta plus del vz by del z k diagonal k. So this is the expression of gradient of V in the polar coordinates. Let's look at another example, a small example of a given vector. So suppose the given vector is u of x is mu of x plus nu x dyadic x a, where a belongs to E3, is a fixed vector, and mu and nu are constants. So what would be the gradient of u? So we can write du as mu dx plus nu, using the product rule of differentiation, dx dyadic x plus x dyadic dx a. This can be taken out, writing this can be written as dx mu dx plus nu x dotted with a dx plus dx dotted with a times x. This part can also be written as x dyadic a acting on dx. Therefore, this expression becomes mu dx plus nu x dot a plus x dyadic a acting on dx. This can be written in terms of the identity tensor plus nu x dot a I plus x dyadic a, this whole acting on dx. Therefore, gradient of u is nothing but mu of I, mu into I plus nu a dot x I plus nu x dyadic a. Let's now look at some quantities which will be needing in our further discussions, which are related to the derivatives. So first is the divergence. So the definition of divergence is the divergence of a differentiable vector field Vx, V of x, V is a function of x belonging to E3, is a scalar field defined by divergence V is equal to trace of the gradient of V. We will look at later what divergence actually means physically. We'll look at a physical interpretation of divergence. So as in terms of the Cartesian coordinates, we have vi comma j, gradient of v as vi comma j, ei diatic ej. Therefore, divergence v becomes trace of this vi comma j, ei diatic ej, taking the scalar term out, becomes trace of ei diatic ej, which is nothing but vi comma j, ei dot ej, according to our definition of trace. This is equal to vi comma j delta ij, and this is vi comma I. Therefore, divergence v with respect to the when written in terms of the Cartesian coordinates is nothing but del v1 by del x1, del v2 plus del v2 by del x2 plus del v3 by del x3. So from our definition of the gradient of v with respect to the polar coordinates, it can easily be shown that in terms of the polar coordinates, divergence v is nothing but vr plus vr comma r plus 1 by r times v theta comma theta plus vr and plus vz comma z. You can show this by yourself. You can calculate this using the expression of the gradient in terms of polar coordinates using the given definition of divergence. The next quantity is curl. Let's look at how it's defined. The curl of a differentiable as these quantities have to do with the derivatives of a vector field. The vector field should be differentiable. That's why it's important to mention that they are differentiable vector fields. So belonging to three-dimensional Euclidean space is a vector field. So divergence was a scalar field. This is a vector field defined as curl of V dotted with C is divergence of V cross C. This is valid for all fixed C belonging to E3 such that del of C is 0, gradient of C is 0. Now an interesting note to take is that when C is given in terms of the Cartesian coordinates CIEI and we have del of C is equal to 0, the 0 tensor, then what does this mean? This means that the CI's are constants. If C is given in terms of the polar coordinates CR, ER plus C theta, E theta plus CZ, K, and then it's written that gradient of C is 0, then what are the restrictions on So this case is not trivial. What are the restrictions on CR, C theta, and CZ? They will not be constants as the Cartesian coordinates. So this I'll leave for you to check. So using the expression of gradient in the polar coordinates, you can easily do this. Equating all the components to 0, we can find the restrictions on CR, C theta, and CZ. Next, we will come to the definition of a divergence of tensor. So this is a quantity which we need further. So the equilibrium equations, for example, have the divergence of the stress incorporated in it. So let's look at how it's defined. So divergence of a, again differentiable, it's important, tensor field A as a function of x belonging to len is a vector, is a vector field. So divergence of a vector is a scalar, divergence of a tensor is a vector, defined as divergence of A dotted with C is equal to divergence of A transpose C. This is valid for all fixed C belonging to E3 such that gradient of C is 0. So let's look at when what the divergence of a tensor is when A is given in terms of the Cartesian basis. So divergence A would be something times E1, something times E2 plus something times E3. These would be divergence A dot E1 and similarly divergence A dot E2 and divergence A dot E3. Basically the components of the vector divergence A. So by definition of the divergence, by this definition, we can put C as E1, E2 and E3 to get the components of the divergence. Therefore, divergence A dot E1 is divergence by the definition A transpose E1. So let's put it out that the as A is given as Aij, Ei diatic Ej, if A transpose is Aij, Ej diatic Ei, and A transpose E1 then becomes Aij, Ej diatic Ei, take out E1, which is nothing but, so this would be Ei dotted with E1, that is delta I1 Ej, and delta I1 multiplied with Aij would be A1j Ej. Therefore, this becomes divergence of A1j Ej, can be written in terms of components, that divergence A11 E1 plus A12 E2 plus A13 E3. Now, by the definition of divergence of a vector, these can be taken individually. By the definition of divergence of a vector, we have what do we have? Vi comma I. So here the Vi's are nothing but A11, A12, and A13. That is V1 is A11, V2 is A12, and V3 is A13. So this becomes A11 comma 1 plus A12 comma 2 and A13 comma 3. Similarly, divergence of A dot E2 is A21 comma 1 plus A22 comma 2 plus A23 comma 3, and divergence of A dotted with E3 is A31 comma 1 plus A32 comma 2 plus A33 comma 3. Therefore, divergence of A can be seen that it is nothing but Aij comma j Ei in terms of the Cartesian components. Let's look at it in terms of polar coordinates. So in polar coordinates, let's say a tensor is given as ARR ER dyadic ER plus AR theta ER dyadic E theta plus ARZ ER dyadic K plus A theta R E theta dyadic ER plus A theta theta E theta dyadic E theta plus A theta Z E theta dyadic K plus AZR K dyadic ER plus AZ theta K dyadic E theta plus AZZ K dyadic K. All these are functions of ARR to AZZ are functions of R theta and Z. So as with the Cartesian case, divergence of A would be some quantity times ER, some quantity times E theta, and some quantity times K. So this is divergence of A, again the components dotted with ER. This is divergence of A dotted with E theta. This is divergence of A dotted with K. So we'll take this term first, divergence A dot K, as K is a constant vector. The rest of the vectors ER and E theta we know are not constant but functions of theta. We'll look at them later. So divergence A dot K is divergence A transpose K, which is divergence of A ZR ER plus az theta e theta plus azz ez. So according to our divergence definition of divergence in terms of the polar coordinates, as we had seen before, which I had asked you to prove, where was it? Next page. This one. With that definition, it can be written as that this is nothing but zr comma r plus 1 by r az comma theta az theta comma theta plus azr plus a zz comma z. Now divergence A dotted with ER, as already mentioned before, is not equal to divergence A transpose ER, because del of ER is no longer equal to 0. So it can easily be shown by our definition of gradient of a vector field that del of ER, I'll leave it for you to check, is 1 by r e theta diadic e theta, and del of e theta, gradient of e theta, is minus 1 by r er diadic e theta. So we already have our definition of gradient in terms of the polar coordinates. Just have to put v as er. So we'll use our identity going further, which will which can be easily proved using the product rule and initial notation. The identity is, we'll look at it in the problem solving session for this topic, that u dot divergence of A, where u is no longer a fixed vector, is divergence of A transpose u minus trace of A transpose gradient of u. We'll see this in the problem solving session. Therefore, taking u to be er, we have er dotted with divergence A is equal to divergence A transpose er minus trace of A transpose gradient of E. Sorry, gradient of ER. So divergence of A transpose ER is divergence of ARR ER plus AR theta E theta plus ARZ K. So again, by a divergence in terms of polar coordinates, divergence of a vector in terms of polar coordinates is nothing but ARR comma R plus 1 by R AR theta comma theta plus ARR plus ARZ comma Z. Now trace of A transpose gradient of ER is 1 by r trace of A transpose E theta diatic E theta. So from our definition of gradient of, from our expression of gradient of ER, uh, this is equal to 1 by r trace of A transpose E theta diatic E theta. This is nothing but 1 by r A transpose E theta dotted with E theta. This is 1 by r A theta theta. This can also be written by taking A transpose on the other side. This is nothing but E theta dotted with A E theta. This is just the theta theta component of A. Therefore, ER dotted with divergence A is ARR comma R plus 1 by R AR theta comma theta plus ARR minus A theta theta plus ARZ comma Z. Similarly, the E theta component of divergence A is divergence of, by using the identity we mentioned, E theta, divergence of A transpose E theta minus trace of A transpose gradient of E theta. So divergence of A transpose E theta is again divergence of A theta of this vector A theta R ER plus A theta theta E theta plus A theta Z. Okay, this is nothing but A theta R comma R plus 1 by R A theta theta comma theta plus A theta R plus A theta Z comma Z, and trace of A transpose gradient of E theta is minus 1 by R trace of A transpose ER, and directly taking the A transpose onto the first vector of the dyadic product E theta. This is nothing but minus 1 by R ER dotted with A E theta, taking the transpose on the other side of the dot product when we apply trace is minus 1 by R AR theta. Therefore, E theta dotted with divergence A becomes A theta R comma R plus 1 by R A theta 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 comma theta plus A theta R plus A R theta, taking this inside the bracket, taking this part, and plus A theta Z comma Z. Now these quantities E theta dot divergence A, ER dot divergence A, the expressions for these, and what was the first one, divergence A dot K, they can be plugged in back into this equation to have the whole vector divergence A. Another method that can be used without using the identity, using our initial definition of divergence in terms of a fixed C, the divergence A dotted with C is equal to divergence A transpose C. C is fixed, that is gradient of C is 0. So C in when written in terms of the polar coordinates CR plus C theta E theta plus CZ K, gradient of C is 0. So we can characterize such C such that C, when given in terms of the polar coordinates, the gradient of C is 0. We can find out what such C are, and then use that definition of C or such conditions on C, use them in the definition of divergence to obtain the desired result. Next, we will look at gradients of scalar valued functions of tensors. So we have looked at scalar fields, that is scalar valued functions of the position x. I will look at a function which is scalar of a tensor A belongs to them. So taking the differential, we can write it as d of g is nothing but del with differentiation of g, partial differentiation of g with respect to a dotted with dA, as this quantity is a scalar and this quantity is a tensor. This also belongs to len. This is a dot product of two tensors. So del A G also belongs to len, which is understood to be the gradient of G with respect to A. So let's look at some examples of these. So for example, if G is the first invariant of A, is the trace of A, this can be written as A dot I. Therefore dg becomes nothing but I dotted with dA, and therefore del G with respect to A is nothing but identity. This was the first one. Let's look at the second invariant, I2 of A. This is nothing but trace of A star, the cofactor matrix, a cofactor tensor, half of trace of A square minus trace of A square. Therefore, G of A can be written as 1 by 2 I1 square minus I dotted with A square. This is A acting upon A. Or dg becomes 1 by 2 to I1 di1 minus I dot daa minus I dot a dA. By the definition of the dot product, these two are equal. So this becomes I1 di1, as we saw, was I dot dA minus I dot daa. So this becomes, therefore dg becomes I1I minus A transpose. And I dot dA acting on A can be written as trace of I transpose dA, which is nothing but trace of dA A. This can be written as, because trace of AB is equal to trace of BA, this is A dA. This becomes A transpose dotted with dA. So dg is I1I minus A transpose dotted with dA. Therefore del A I2 is I1I minus A transpose. This I1 is trace of A. Looking at the third invariant as well, G is equal to determinant of A. So we assume that A is invertible, that is determinant of A is not equal to 0. So using our original definition of determinant in terms of the box product AA, AB, AC divided by AB, box product of AB and C, such that ABC are linearly independent, such that the box product doesn't become 0. So taking a differential of this becomes dA acting on A dotted with AB cross AC plus dA acting on B dotted with AC cross AA plus dA acting on C dotted with AA cross AB divided by the box product of ABC. Now, according to the definition of the cofactor, this can be written as cofactor of A acting on A cross B. This is given the fact that A is invertible. Therefore, dg can be written to be 1 by box product of ABC times dA acting on A dotted with A star B cross C plus dA acting on B dotted with A star C cross A plus dA acting on C dotted with A star A cross B. This cofactor can be taken on the other side as transpose. This becomes ABC A star transpose dA acting on A dotted with B cross C. This can be written in terms of the box product directly, that this is nothing but A star transpose dA A B C plus A comma A star transpose dA B C plus A B A star transpose dA C. This is nothing but the trace of A star transpose dA, which is I dotted with A star transpose dA, which is A star dotted with dA. Therefore, dg is equal to A star dotted with dA, and therefore the gradient of determinant of A with respect to A, with respect to the tensor A, is nothing but the cofactor. So summarizing the gradients with respect to the tensor A of the three invariants of the tensor A, that del A of trace A is I, del with respect to A of trace A star, which is nothing but the second invariant of A, is I1 I minus A transpose, and del with respect to A of determinant A is the cofactor. The last discussion for this topic, we'll start on a new. Okay. Last thing we will discuss for this topic are some integral theorems. So these will be needing regularly for our discussions when we start with kinematics, balance laws, and constitutive relations. The first one is the localization theorem. So let phi be a continuous function defined on some open set R, which is a subset of E3. So we are talking about a region R in E3 if integral phi dv is the integral of phi on the volume, say pi, is 0 for all closed sets pi subset of R. So say take a set here, this is pi, this can be pi, this can be pi, this can be pi. So all closed sets pi which are subset of R, so that is all the pi's taken together cover the whole region R, then phi is 0 over R. Will not give out the proof of this. This can be the proof of this requires a bit of analysis, bit of involved mathematics. The proof can be checked out here on this website, home dot on this URL rather, itk.ac.in eg papers balance loss .pdf. Next, we'll look at the divergence theorem. So let R, subset of E3, be a domain in E3. This is again a region in the three-dimensional Euclidean space with boundary defined as del R. So we have a region R in E3. This boundary is del R and a vector pointing outwards. The normal vector pointing outwards is written as n. So let us have three fields. Let f be a scalar field defined on R. Let p, small p, be a vector field on R, and let A be a tensor field on R. We'll assume all the fields to be differentiable. Then the following relations hold true. So for the scalar field, gradient of f, the volume integral of gradient f taken on the region R is nothing but the f times n dA on the boundary, where n as defined before is the unit normal. So the norm is equal to 1, which is outward to del R. So when we come to the vector field, the divergence theorem becomes divergence of P dV integral of the volume integral of divergence P is nothing but P dotted with N, area integral of P dotted with N over the boundary of R. And the third one relates to the divergence of the tensor field, as divergence of A dV is equal to A acting on N dA. The area integral of A acting on N, which is a vector on the boundary of the region R. So in these terms we will look at a physical interpretation of the divergence. So for example, we have a region R and we have a point x0 belonging to R, and we take a small neighborhood omega for which the outward normal is n around the point x0. So calculating the divergence of the vector field at x0, this can be given by the mean value theorem. Limit v of omega, the volume of omega tending to 0, 1 by v of omega times the divergence of v acting on the integral volume integral of divergence of v on omega. Omega is a subset of R and x0 belongs to omega. So we are looking at the divergence of v at the point x0, that can be approximated as the volume integral of divergence v over omega divided by the volume of omega, and taking the limit volume of omega tends to 0. This is obtained by the mean value theorem. So using our divergence theorem, divergence this one, the second one, we can write the right hand side as, so divergence v at x0 is limit v of omega tending to 0, 1 by v of omega integral del omega v dotted with n dA. So what is this quantity? So this is nothing but the flux of v over del omega. So it is the quantity v dotted with the outer normal, taking an area integral of the whole, taking an area integral over the whole surface. So this is basically the basically how much the quantity goes in or out from omega. That is the flux of v. Let's come to the last of the integral theorems, which is the Stokes theorem. So let P be a differentiable vector field over R, again defining a region R, subset of three-dimensional Euclidean space. So let this be the region R. So we'll consider a surface S. The boundary of this is the curve delta del S, and normal to this surface at each point is the normal. This is the unit vector capital N. So for any surface S in R with unit normal to the surface N, and boundary del S, this relation is valid, that area integral of the curl of P dotted with N is nothing but P dot the line integral of P over the boundary of the surface. Dx is the infinitesimal line vector along del S. So with this, our discussion on tensor analysis or tensor calculus comes to an end. Next, we will look at a few problems regarding this topic, and then we will go on to our main discussion on continuum mechanics. So this brings us to the end of mathematical preliminaries needed to tackle the subject. Thank you.